Okay? I mean, if you, for example, in Peter's book, there is a, for example, 4.4 section, there is a large list of different kind of SDEs and what are their solutions actually. Okay? So, I mean, if you want to practice them, these are very good, what do you call, ways to practice them. Okay, so here is some more terminology. So, I'm going to call that my SDE is SDE of additive type actually. So it contains the additive noise. Okay? So an SDE of this type is going to be an additive type noise actually. Okay, so for example, if it is linear, so A1 xt plus A2 dt plus b of t dw. Okay? So by additive noise, what I'm going to mean that in the diffusion does not depend on x of t. Okay? So the diffusion does not depend on x of t. Alright? So it depends only on time actually. So any of such kind of SDE will be SDE of the additive type actually. Okay? Then if you for example, okay, get into these notes, it gives a different example. For example, it says that let's take dxt as minus alpha xt dt plus sigma dwd. Remember, we call this the Langevin equation actually. So that's really the Langevin equation. Okay, and it's an equation with the additive noise actually. Equation with the additive noise. So, and what was the solution of it? We can drive it easily. So we last time discussed that that's a linear SDE for how to solve it. Okay, so you need to first compute this fundamental solution. Okay, by fundamental solution I mean, the solution of a homogeneous solution actually. Okay, and then using this fundamental solution, a formula that was written in the terms of integral, okay, you can compute the solution of SDE. And if you remember, we constructed the solution for this. And xt in this case was e to the minus alpha t, okay, e to the minus alpha t, x naught plus sigma, okay, x naught plus sigma, 0 to t, okay, e to the alpha s and dws. So this was, kind of solved by us in our, previous two lectures. Okay, so one of the equations was this that we solved. And then in the book you will find a lot of other examples. So in other words, just solve these examples. So these give you kind of a more confidence that how to solve the linear SDEs with additive noise. Okay. And what the strategy would work. So last time we considered the generic linear SDEs. So you can use that strategy that we used in our last lecture to compute the solution of linear SDEs with additive noise. Okay. Then what would be the meaning of linear SDE with multiplicative noise? Okay, and the problems with multiplicative noise are more complicated. Okay. At the moment, I'm just considering the computational dynamics of it. For example, when we'll do some applications of it, you will see that the drift and diffusion has a beautiful meaning. Okay. By additive noise, I mean that drift is something that is deterministic. Okay. While if you have, if the drift also depends on x of t, you're going to call that, okay, that's an SDE with the multiplicative noise actually. Okay. And hence the drift itself becomes stochastic. And that's like adding another layer of complication into the problem actually. So any SDE of this form, bxt a1 a1 xt plus a2 dt, b1 xt plus b2 dwt. This is the equation with the multiplicative noise, because with the noise term, with the Brownian motion, you are multiplying a function that depends on x actually. Okay? So this diffusion itself becomes, what do you call, stochastic actually. Okay? And we also know how to solve such kind of equations. So we also know how to solve such kind of equations. I'm not getting into it. So, and there are plenty of examples here. Okay. So you have SDEs and solution given, so you can really try to solve the solution with the strategy that we discussed in last class and see that whether you get the same solution as these or not. Okay. Then I'm moving to some of reducible SDEs of the specific form actually. Okay? Not generic form, but reducible SDEs of a specific form. So imagine you have an SDE of this form. So bxt equal to 1 over 2 b of xt, okay, and then b prime of xt dt plus b of xt dw. Okay, and d is could be a nonlinear function as well. Okay, so therefore this SDE is really a nonlinear SDE. Obviously, since the b is a function of xt, so it's an SDE with the multiplicative noise. Okay, SDE with the multiplicative noise. So if you have this form of an SDE or this kind of an SDE, okay, then you have some known kind of solution for this kind of problems actually. So what can be shown is that this kind of SDE or the solution of SDE can be computed, or solution can be computed as this actually. So the xt can be written as the H inverse function, and I'm going to tell that what is H inverse or what is H, evaluated at wt plus H of x naught actually. Okay, some usual condition where H of x can be computed by integrating over the domain, say from 0 to x ds over p of s actually. Okay. So, and how this solution is obtained, on the same algorithm that how to reduce a nonlinear SDE into a linear SDE and then solve it actually. Okay, the previous algorithm. I know there is a lot of waving of hands, but all this will be clear once you will start reading from. Once you will carefully make sense of this reducible to linear SDE. So what is this telling you? Imagine you have an SDE of this form, so in which you have a function, so half of a function multiplied by its derivative, and the same function appears in the drift as well, then the solution of such problem can be written as this. So what you need to do in order to compute the solution, so first you need to compute the H, okay, and H can be computed by take this B and integrate it, and that will be now a function of x. And then we know how to compute the inverse of it. Okay, compute the inverse of it and evaluate, that inverse at this number actually, wt plus h naught, and that would be the solution of given as d. For example, here's one example actually. Here's one example. So imagine you have this seemingly looking nonlinear SDE. So a times a minus 1/2 and xt 1 minus 2 over a dt plus a xt 1 minus 1 over a dw. Okay, so imagine you have this kind of an SDE. So my claim is that if you take, okay, so let's assume for now that I somehow, okay, but I can know actually that if you, for example, take this, the process in the diffusion and define, for example, a b corresponding to it. So the b is going to be ax 1 minus 1 over a. So this is really going to be the b of x or the b of s, right? And you can see that if you compute, for example, b prime of x, so it's going to be what? So it's going to be a times 1 minus 1 over a, okay? And then you have x raised to
minus 1 over.
Okay. X raised to what? 1 minus 1 over a minus 1, right? And this, right? And now, if you, for example, multiply the b of x and b prime of x, so what are you going to get? So it's going to be a square 1 minus a over a. Okay, is there something missing? No, there isn't anything missing. Over a, and x raised to what? X raised to 1 minus 2 over a. 1 minus 2 over a, right? And you can get rid of this and this, so you have a times this actually. Okay? So you can really see that you are having, I mean, if you see it without 1/2, then this is really the same function.
Sir, this one must be 1 minus a or a minus 1.
You know the
ये जो a times
a minus 1, yes. Okay. A minus 1. ठीक है? Isn't that good? So again, it's like guessing that what kind of form does it have actually. And once you have it, then how you can solve it? So in order to solve this, what you need to do, so you need to compute first h actually. Okay? So you need to compute h of x, and h of x would be that you integrate, for example, from 0 to x this ds over b of s. This would be 0 to x ds, and my b of x is b of f is a s and 1 minus 1 over a, right? And this would be 1 over a and what? Integrating, okay, so integrating from 0 to x, s 1 over a minus 1 ds, okay? And 1 over a, s is going to be s 1 over a minus 1 plus 1, and 1 over a minus 1 plus 1, so these two guys will go away, This will go away.
S power.
0 to x, so it's going to be x raised to 1 over t. Okay. This is h of x. So what would be h inverse of x? So it's going to be always x raised to a. Okay. So it's going to be h inverse of x. So hence the solution to the SDE, the formula, the solution to the SDE is that you evaluate your h inverse function at this point actually. So this is going to be what? Wt plus what? H of x naught, so it's going to be x naught raised to 1 over a and everything raised to a. So that would be really the solution. Is it making sense? Okay. It's not really difficult. The thing is that, yes, there are special kind of SDEs that you can solve analytically. So that's really an analytical solution. Okay. And I mean, if you go into the book, then there are plenty of examples. There are really plenty of examples. So I'll say that do at least some. Okay. And the meta conclusion of this discussion should be that okay, there are some kind of SDEs for which you can really analytically solve things. Okay. But they are very limited, obviously. So linear can be for sure solved, and non-linear, there are some kind of non-linear things that you can solve. Okay. Let me write two more forms of SDEs. I'm not going to solve, like do one examples with them. I'll just mention the form and their solution. You have to do it for yourself. And then do some examples relevant to those as well. So another kind of SDE that you can reduce linear SDE is this. It's of this form. It's of this form. So imagine you have this e to SD that goes like this. So dxt equal alpha b of xt plus b of xt b prime of xt half dq plus b of xt and dw. Okay, so this is also a nonlinear SDE with multiplicative noise. And what is the difference between the previous case and this case is that now an additional in the drift term you are adding some constant times of b of xt. Okay. Then such kind of equation is also reducible to a linear type SDE. Okay. I'm not writing at the moment that linear type SDE. So that linear type SDE is really going to be something of this form: dxt alpha b of xt plus b of xt, Stratonovich noise with the dwt. So our next topic is going to be to go through this Stratonovich type thing. If you don't understand it now, it's okay. Okay? So it will turn out to be such kind of an SDE, and its solution. Okay, its solution and its solution
413 equation
can be written as h inverse of alpha t plus wt plus h of x naught. Okay, where the h is same as the previous case. H is not changing. Okay? H is not changing. The idea really is that the thing that I mentioned previously are the things that you are going to study, for example, in this theory, that how to reduce a nonlinear SDE into a linear SDE, that you turn this SDE into this Stratonovich type SDE. And then in a moment I'm going to give a brief description of it, that what do you mean by an SDE driven by an Stratonovich noise. You will see actually that we can rewrite this SDE in the terms of following linear SDE actually. So d by t equal to alpha dt plus dwt. Okay? In other words, by taking a one transformation, which is yt equal to h of xt, so if you take this transformation onto this, SDE of the Stratonovich type, then it will turn out to be the linear SDE. And by solving this linear SDE and computing the xt, I can find yt. So the yt would be what? So yt is going to be this actually. If you're going to solve this linear SDE, the yt would be this. But yt is h of xt, so you want to find xt. So you need to take the inverse of it in order to find the h of xt. Okay? So go through this section. It's a fun section. It talks about many different things. And then there are some more type of SDs that are mentioned, so you can read them for yourself actually. Okay. So there is another third kind of a SDE, which is a bit generalization of this. That along with b of xt, imagine that you also have an h of xt. Then how to solve it? You can also reduce that kind of SDE into a linear SDE and then solve it. So, so there isn't stuff for you to read. Just go through them, read them, do some examples, and keep some of the results as fact. And this is what the really key thing. So I can't guarantee that, for example, when you are modeling things through stochastic differential equations, so how much of these trick would works for you? No idea. Okay. In some situations, these tricks can work, and they will work. For example, in finance, there are plenty of SDs which can be really done with such kind of strategies. But if not, we always have numerics.
सर फिर इनके लिए स्कीम्स अलग होती है
इनके लिए
न्यूमेरिकल स्कीम
इनके लिए भी schemes वैसे ही होती है. So there, like you have Euler scheme and Rangakata scheme. So you also have, Euler scheme for example, stochastic SDEs, and then you also have Euler scheme, Milstein scheme for example, SDEs. So I have said, Sai Adarshah to give you a time. So I was saying that I should give you time on this subject, but then he said that I'm busy. Then I said, okay, give some time in next. So one class that is remaining for 3 hours, I'm going to say him to give you an overview of it. So he's going to at least tell you that how to simulate Brownian motion and some of SDs driven by Brownian motion quickly. I think we're not going to get time actually. Okay. At least you should know some basics of it. I mean, if you want to read, then like numerical solutions of SDEs and stochastic differential equations and PDEs is the entire area. Like we have the numerical analysis for PDEs, and it's an entire area. So we have also something similar as well. Alright. So, enough of SDs. Let's talk about some more interesting results. I would like to talk about a noise of Stratonovich type. Then what do I mean by that? How to compute the integrals of a Stratonovich type and so on and so forth. So, in my thesis, I used a lot of Stratonovich type noises because when you are doing geometry, they are very helpful type kind of noises. Alright. Here's a quick thing. So what do you mean by Stratonovich integral and Stratonovich type classic? Stratonovich integral. Okay. This type of noise is very useful in many different situations. I found it very useful when I was doing geometry. So here's the definition. Here's the definition. Imagine I have two Ito processes, xt and yt. Processes, then Stratonovich, integral of xt with respect to yt can be written as this. So I have to integrate, say for example, from A to B, a process xt with respect to an other noise which is dyt. Okay? I don't have to compute it in a normal manner, but in a Stratonovich type manner actually. Okay, so whenever I'm going to put a circle in between this xt and differential, I'm going to mean a Stratonovich integral of xt with respect to dyt. So what do you mean by this actually? So what is the meaning of this? The meaning of this is simple. That you take A to B, compute your integral with respect to yt. So